Hello everyone. In this video, we will show you that how can we rotate vector x with twice of the angle between a vector a and b. And we will achieve the rotation with the reflection we talked about from previous video, and we will use the reflection twice, which we will call double reflection. So as you know from the previous video that if we want to reflect, for example, x here, and with respect to a, and we will get a x here, that x star, and the reflected vector, where is the reflected vector pointing? It depends on where's the vector that with respect to pointing. So if we have the same vector x here, and if the vector a is here, then we reflect it, it will be like here, right? So on the intuition, it doesn't sound right that we can use a double reflection, because we want to reflect a vector with an angle, and where a and b point to should not matter, only the angle between them matters. But a single reflection shows that, well, where this a point to, it matters. So we are going to ask a question: can we actually achieve a rotation with a double reflection? So the question we should be asking is, does where a and b, vector a and b point to matters? So let us see that what happened in double reflection in a 2D case. So first we have x. We look at this as a case 1. We have vector x pointing on this direction. When we have a and b, that let us for simplicity's sake, we just make it 90 degrees. So we try to reflect a, then we reflect with b. So this is x, and this is a, and we reflect respect to a, so we get this called x prime, and then we reflect respect to b. So x prime reflect to b, it will get this. This is x star, that let's say x prime, yeah. So we can see that the x prime is a 180 degree to the original x, which is the twice of the angle of 90 degree. Okay, now it seems we can this makes sense in case 1, but what happened in case 2? That let us say we have a pointing upward and b pointing to the left, and the angle between a and b are still the same. So what happens if we reflect x respect to a and b again? So let's say this is a, and this is x. So here reflected, we get x prime, and then b is here. So then reflected respect to b. Oh, I should using dot. So this is x prime prime. Now you can see that this is almost 180 degree, where it looks like a 180 degree, and we have 90 degree between A and B, and we have rotated twice of the angle between A and B. So so that to answer this question, you can see that the case 1 and case 2, A and B, the angle is the same, but they are pointing in different direction. And in this case, we only use a 90 degree, but if you try it for any degree, any different degree, where A and B point to does not matter. However, what matters is how A and B relatively point to, which we fix the angle between them. So to answer this question here, does not matter. Does not matter. However, how they relatively point to relatively relatively point to, that matters. So this gives us the expression. We know how can we do the reflection. For example, reflect with A, right? We use x A inverse A, and then we reflect with B inverse B. So this is like a sandwich product. So we can actually, since geometric multiplication is associative, so we can calculate A, B, and B inverse A inverse A inverse. So this is the expression in geometric algebra, how you rotate a vector with twice of the angle from A to B. And generally, people are referring this to thing as a rotor. From the previous slide, we have expression to rotate x with twice as much angle from A to B, and that will be the B inverse geometric product with A inverse, geometric product with x, and geometric product with A, and geometric product with B. And then now we want to simplify this expression a little bit by assuming our vector A and B have length 1. So assume that the dot product, the length, which is in the length square, which in D is the dot product B dot B, is equal to 1, and also the length A square is equal to A dot A is equal to 1. Recall that the definition of inverse, B inverse, defined as B and B dot B, and that in our case because the assumption it will just equal to B. And also that A inverse is defined as A dot A equal to, because A dot A just 1, we assume that the length has 1, so it would just be it would just be A. So since we are working with a unique length now, X is not unit length. X can be different length and point in different direction, but A and B has length 1. So we will use this notation, a hat, to indicate a vector. A is a vector which has length 1 is a vector that has length 1. This is the same thing for B. So we can rewrite this expression. So B hat, A hat, X vector, and A hat, B hat. That will rotate X with twice of the angle from A to B. This means that if X is pointing upward here, this is the X, and let me draw it bigger, and A is pointing here and B is pointing here, that is A and that's B, and inside is a 45 degree, then this will give X, since A to B is 45 and twice of the angle will be 90, so the rotated X will be point to the left. Oh, it's too long. It will give us vector like this. This is a rotation achieved by reflection, a double reflection, which you reflected twice. This slide is for the people that know the Euler formula from complex number theory. And if you don't know this, you can skip this slide. So if you know the complex number from Euler formula, it turns out we can express the rotation, which is actually a double reflection, into a Euler formula. But this a little bit changes is that here is the bivector B, and it is a unit bivector such that the bivector geometric product to itself is equal to -1, and that bivector can be always generated by two vectors wedge each other. So I'm not going to prove this equation for all the dimension, and we will only look at for the case, for example, 2D. If we think about, we have expression A hat, B hat, A hat, X, sorry, not X hat, but X vector, and A hat, B hat. And we're only focusing on this part. We have A hat, B hat, and we know that the geometric product between them will become, you can I'm not going through the detail, but it will be a cosine the angle between them from B to A, this angle called I think this one is per C, and plus it will be the sine. Let's see, where is the E12, which is the bivector, E1 and E2. And here there's no vector. This is just a scalar, which is 1. I can write a 1 there, so to tell me that the basis here is a scalar, and this term, the basis here is a bivector. And we know that this bivector 1, 2 and geometric product E1, 2 is equal to -1. Then we have everything we need to be written as in the Euler formula. So A hat B hat is equal to E per C and E12. And remember that we define the per C was defined as here's A and here's B and A hat, B hat. So this angle and A hat, B hat was defined, the per C was defined from B to A, but here we have this expression is from A to B, and we would redefine this to minus theta. And since we will rotate this twice, well, we want the theta to represent the total angle we rotated. So the per C we will express the per C into the -1 theta divided by 2. So it will become 2. It will become this exponential minus theta divided by 2, and with a bivector 1, 2 basis. And you can see that this is why we can write it in this way. And B and A will give us, we will using a similar story. I already assumed that you're familiar with the Euler formula and from the complex number theory, that you know why the cosine and sine, cosine 1 and sine with someone that multiply itself equal to -1 can be written into the exponential. I already assume that you know this. So here, B hat, A hat we will use a similar argument. Then we end up with E theta divided by 2 and E12. So this is the case in 2D, and for the case in higher dimension, we also need to make sure this statement holds. And the philosophy behind this requirement that this bivector must be able to be generated by 2 vectors is that we need the bivector B to be represent a rotation plane. And some bivector, for example, let's say B hat prime, if a B hat prime was equal to E12, in 4 dimension. Now we go to the 4 dimension, E12, E34. Well, you cannot find any bivector. No, you cannot find the B hat prime can be expressed. You cannot find, so it's not equal to Q, which P, even though Q and P, vector Q and P is in 4 dimension, because such such linear combination of bivector does not represent a rotation, and this happens when you're starting working on the you starting working above 3 dimension, which things can be happen in 4 dimension, 5 dimension, 6 dimension, but in 2 dimension and 3 dimension, this requirement is not this requirement will be always satisfied. So any kind of bivector in 2 dimension and 3 dimension can be expressed by the wedge product of vector and another vector. So this is the special case when you're working above 3 dimension, which is 4 dimension, 5 dimension, and so on. So thank you for watching all the video. You are now watching this slide, so I guess you have watched most of my slide. I know this video series has not been perfect and quite a lot of things to be improved. This is my first time making educational video series online. I'm currently learning projective geometry algebra. Only if I can understand it, I may make a video series about it, and hopefully it will be a better one. It motivates me to learn and share more when people think what I have shared is valuable. So, if you like what I have shared, leave a comment. If you also found that my understanding is incorrect, please leave a comment too and let me know. I'm happy to correct and learn more. I want to thank people from the Discord channel called Bivector. When I do not understand something, I will ask question there, and most of the time, I will have answer. Thank you and have a nice day.